Get ready. Design junkies to torque your nuts, harden your springs, and forge that mind into a bulletproof study guide. We are mechanical engineering made simple. Welcome back. Today we are strapping in for a deep dive into the structures that, literally hold our industrial world together. Shells of revolution.
That's right.
We're talking pressure vessels, huge pipelines, complex containers, basically anything built around a central axis.
Yeah.
Cylinders, cones, spheres.
And the thing is, the real complexity isn't the shape itself, it's about how that shape behaves under massive loads, either from the inside or the outside.
Right.
So our mission today, really, is to extract the essential knowledge. We need to understand the difference between the simple baseline stresses, what we call membrane stresses, and the much more dangerous bending stresses.
Especially when you start joining different shapes together.
That's where things get critical. We're going to look at how engineers handle those joints to prevent catastrophic failure.
Because to most people, a tank is just a tank.
Hmm.
But to an engineer, if those stress calculations are off by even a tiny fraction, it's a bomb.
It absolutely can be.
So let's start with the ideal scenario. The engineering dream, which is the thin shell. What's the actual dividing line? When is something officially thin?
Okay, so the rule of thumb, the definition we use, is that a vessel is thin-walled if its wall thickness, let's call it T, is less than about 1/10 of its smaller principal radius of curvature.
The 1/10 rule. So if you meet that criteria,
Yeah.
what does that buy you analytically?
It buys you a massive simplification, a huge one. If you're thin and the load is smooth and evenly distributed, axisymmetric,
Right.
you can essentially take a complex 3D stress problem and boil it down to a 2D one. You get to completely ignore the stress acting through the thickness of the wall.
Okay, so that means we're left with just two main forces to worry about, right?
Yeah.
Pure tension running along the wall.
Exactly. We focus on just two membrane stresses. The first is the meridional stress, S sub 1. Think of that one running along the profile, like from the North Pole to the South Pole of a sphere.
Got it. Top to bottom.
And the second is the circumferential, or hoop stress, S sub 2. That's the one acting around the circumference. It's the stress that tries to blow a barrel apart sideways.
And just to be clear, the radial stress, S sub 3, and any bending are, basically zero?
For all practical purposes, yes, they're negligible. If everything is perfectly symmetrical, every circle just wants to expand or contract uniformly. There's no internal force trying to bend or warp the wall.
Which is why there are standard off-the-shelf formulas for these simple shapes.
That's membrane theory in a nutshell. It's the beautiful, simple starting point.
But of course, the real world is never that simple. You don't build things out of infinite isolated spheres.
You definitely do not. And that's where the dream ends and the real engineering begins. The moment you introduce any kind of real-world imperfection, membrane theory starts to break down.
And these significant bending and shear stresses just pop up out of nowhere.
They do. And there are a few key triggers for these so-called discontinuity stresses.
Okay, what are the big culprits? What kills the simplicity?
Well, first is any kind of concentrated load. So instead of smooth internal pressure, imagine a heavy support bracket welded to the side.
A point load.
Second, and this is a huge one, any abrupt change in the geometry, a sudden change in wall thickness, or welding a flat plate onto the end of a cylinder. Any sharp corner.
Makes sense.
Third is any geometry where the wall starts to become normal to the main axis, like the very edge of a flat-topped tank. And the fourth, which we'll get to, is just being too thick in the first place.
But that second one, the joint between two different shapes, feels like the most common problem you'd run into.
It's unavoidable. Take a standard pressure vessel. You have a cylindrical body, and it's capped with a spherical or elliptical head.
Why is that joint such a headache?
Yeah.
Even if the pressure and the material thickness are identical.
Because under that pressure, the two parts want to grow by different amounts.
Oh.
Think about it. The simple formulas tell us that a cylinder expands radially based on its hoop stress. A sphere expands uniformly in all directions based on a totally different equation.
So the cylinder wants to flare out, say, 1/100 of an inch.
Right.
And the spherical cap it's welded to only wants to expand by, 8/1000ths of an inch.
Exactly. They fundamentally disagree on how big the opening should be. And that mismatch, that tiny difference in radial deformation, is what creates the problem.
So the material itself has to bend to keep the joint from ripping apart.
That's it, perfectly. To force those two edges to stay continuous, the structure generates its own corrective forces, localized bending and shear, right at the joint, We call it deformation matching.
Which means that the simple membrane stress numbers are useless in that area. You have to account for the bending. I remember seeing a wild example, a toroidal section, that's like a donut shape, right?
Yeah, the knuckle region.
Where a pretty low pressure, just 200 pounds per square inch, actually caused a negative change in radius. The part pulled inward by 0.02 of an inch at a certain point.
And that tiny, tiny movement is everything. It's the physical manifestation of that massive bending stress. This leads to a really powerful analogy that engineers use.
Okay.
The math for analyzing these cylindrical shells is basically identical to solving problems for beams on elastic foundations.
Whoa, okay. That sounds like a completely different universe.
Yeah.
How is a pipe under pressure the same as a beam sitting on a bunch of springs?
Well, think about the beam. It's supported along its whole length by something that resists being pushed down, right? The springs.
Right.
In the shell, the beam is the wall itself running lengthwise. And the elastic foundation, the springs, is the continuous circumferential stiffness of the rest of the shell. The hoop strength is what's providing the support.
So the rest of the pipe is acting like the springs, resisting any local deformation.
Precisely. And this is a huge deal because it means engineers can just borrow all the well-established solutions from beam theory. You just swap out the beam parameters like beta and EI.
The moment of inertia.
Yeah, you swap those for the shell's parameters, specifically a value called lambda, the characteristic length, and d, the flexural rigidity of the shell wall.
And what does that flexural rigidity, D, represent?
It's the shell's inherent resistance to bending. It's a function of the material's elasticity and, crucially, the cube of the thickness. It's an incredibly powerful shortcut.
That's a clever way to manage the complexity. So let's see this in action. If we're welding, say, a cylinder to a cone, how do you actually calculate those corrective forces?
The method is called superposition. You basically solve two simpler problems and then add the results together.
Okay.
Problem 1 is the ideal case. You calculate the deformation of each part separately using just the simple membrane formulas for the internal pressure.
So you pretend they're not connected and see how they want to flare out on their own.
Exactly. Then problem 2 is the corrective part. You add an unknown shear force, V0, and an unknown moment, M0, right at the edge of each piece. And you solve for the V and M that would be required to bend them back so their edges line up perfectly.
They have to match in both position and angle.
Position and slope, yes. They have to meet seamlessly. And when you do this, the results can be just staggering.
I think I know the case study you're talking about. The vessel with the 24-inch radius cylinder and the 45-degree conical ends.
That's the one, under just 300 psi of internal pressure.
Okay, so first, what was the simple membrane stress, S sub 1, in the cylinder if you just ignored the cone attached to it?
The baseline stress, but only 5,690 pounds per square inch. A very manageable number.
The number you might use if you didn't know any better.
The number that would get you fired? Or worse.
Oh, what happened when you added in the bending effects from the junction?
The combined stress on the inside surface of the cylinder right near the weld skyrocketed. It jumped to a tensile stress of 42,260 psi.
Wait, 42,000? Compared to 5,600, that's, what, almost 8 times higher?
It's a massive stress concentration. The bending stress caused by that joint was monumentally larger than the simple membrane stress. The design would have been dangerously inadequate.
And on the outside surface, it was actually in compression, right?
Right, a compressive stress of over 30,000 psi. That huge swing from high tension on the inside to high compression on the outside. That's the signature of a powerful bending moment at work.
That is genuinely terrifying.
Yeah.
For even more accuracy, there are things called correction terms.
Yes, especially for thicker, high-pressure vessels. The simple models assume the pressure acts on the theoretical center line of the wall.
But it doesn't. It acts on the inner surface.
Exactly. And when you join two parts with maybe a slightly different thickness, you create a tiny internal step at the weld.
Ah, and the pressure pushes on that little step.
It does. And that creates tiny radial and axial forces that the basic theory misses. These correction terms account for the real physics of the pressure acting on that internal geometry. They can be critical for safety in extreme applications.
The level of detail is just amazing. Okay, so let's shift gears. Let's throw out the thin wall assumption entirely. What happens when we get into thick-walled vessels?
Now you're in a different domain. The biggest change is that the radial stress, S sub 3, is no longer 0. You absolutely cannot ignore it.
It varies from the full internal pressure on the inside surface down to 0 on the outside.
Correct. And the other stresses, S sub 1 and S sub 2, are no longer uniform across the wall either. They vary. And this leads to a really strange counterintuitive limit.
Which is?
For a very thick cylinder under extreme pressure, you reach a point of diminishing returns. If your internal pressure, Q, is already equal to the maximum allowable stress of your material, S,
Yeah.
you cannot make the vessel safer by adding more thickness. No matter how much thicker you make it, the stress on the inner wall will never drop below S.
So you can't just throw more steel at the problem. You need a smarter approach.
You need to get creative. You need to induce residual stresses. The classic methods are shrink fitting or a process called auto-frettage.
Auto-frettage. That sounds aggressive.
It is controlled damage. You intentionally overpressurize the vessel so much that the inner layers permanently stretch. They enter the plastic range.
Okay.
Then, when you release the pressure, the outer layers, which were still elastic, spring back and squeeze the now oversized inner layers. This leaves the inner surface in a state of high residual compression.
So when you put it into service, the internal pressure first has to fight through that built-in compression before it can even start to put the material into tension.
You've got it. It effectively cancels out the highest stress. The shrink fit method we saw required calculating a precise interference fit, something like 0.003 of an inch. That tiny difference controls the entire vessel's capacity.
That's all for internal pressure. But you mentioned a completely different failure mode that comes from the outside.
And this is so important. External pressure is a whole different beast. It's compressive, and compression can lead to buckling or instability failure.
The structure just collapses.
It collapses catastrophically, often at a stress level far, far below the material's actual strength limit. It's not a strength failure, it's a geometric one. And your standard stress formulas will not predict it.
And the example for this was a corrugated tube, something that seems pretty harmless.
Exactly. For a tube with 60 corrugations, the calculation showed it could become unstable and squirm, that's the technical term, with an internal pressure of just 96.3 psi.
That's nothing.
It's very low pressure. The geometry, not the material strength, dictated when it would fail. It's a huge lesson.
It really is. I mean, we've gone from the clean, simple world of membrane stresses, S sub 1, S sub 2, to the absolute necessity of localized bending analysis at every single joint.
And then realizing that just making things thicker has its limits, which forces us into clever pre-stressing techniques.
And finally, acknowledging this lurking danger of geometric instability, which is a whole separate field of analysis. The amount of work required for a truly safe design is immense.
It really shows that mechanical design is all about the deep relationship between stress, geometry, and deformation. You can't separate them.
Which leads to a final thought for our listeners. We know material science gives us a hard limit, a maximum stress any material can take. So given that, what role does intentionally creating controlled, damage-inducing residual stress with something like auto-frettage play in pushing the boundaries of what's possible? How much more performance in life can we squeeze out of the world's most critical high-pressure vessels by essentially pre-stressing them at the factory? And maybe more importantly, how much risk are we unknowingly accepting every time we rely on a simple calculation that ignores the complex reality of a joint? That's the deep dive you have to continue on your own.